All right, so we're going to look at a couple examples of the what's called the second derivative test. So we use the first derivative test to locate mins or maxes. So with the first derivative test, you found your critical numbers of your function. So a critical number had to be defined for the function. And then you either had a horizontal tangent at that particular point, we call that a critical number, so that would be the first derivative is equal to 0, or the first derivative does not exist. Those were our critical numbers, and we would test around looking for increasing or decreasing behavior to locate mins or maxes. The second derivative test is also can be used a lot of times to find extrema. So the requirements is we let f be a function, and it's going to be twice differentiable. We'll say such that f prime of c is equal to 0, and here's the twice differentiability, f prime double prime of x exists. So the first thing we need is f prime of c to equal 0. When f prime of c equals 0, that means we have a horizontal tangent at c. And a lot of times we're going to have a min or a max there. We can't have the other part of the critical number, whereas the derivative did not exist at that point. Because if the derivative does not exist at that point, then I can't take the second derivative at that point. Because if the second derivative existed, then that would mean that the first derivative should have existed, and it should be continuous at the first derivative, and it's just a mess. So don't go there. Anyways, and so f double prime of x exists on an open interval that contains c. So if f double prime is greater than 0, then you might be thinking, oh, well, that's going to be a max. And you're wrong. It's a min. And we'll draw a picture. And it's going to be a min at c comma f of c. And remember, the original functions are position functions. So if I'm talking about location of mins and maxes, I'm going to plug in c into the original function. Okay, so here's our horizontal. Here's our maybe it's like a parabola or something. You see that horizontal tangent at c, and that shows us that we have our first derivative is equal to 0, and then we have concave up, so we have a minimum at that point. And then similarly, if our second derivative is less than 0, we have a relative max at that location, c comma f of c, and I'll draw you an accompanying picture for that. We'll put in our horizontal tangent, there's our c, and then our graph's opening down. And then finally, if our second derivative is equal to 0 at c, then we don't know. It's inconclusive, and probably our best bet is maybe to go back and use the first derivative test. So kind of like the overview of using the second derivative test, you're going to take the first derivative, you're going to set it equal to 0, and you're going to find they're kind of like your critical numbers, but we rule out the ones where the first derivative is undefined, so it's just where your first derivative is equal to 0. We take the second derivative, and then we plug in those numbers and see if we have positive or negative or concave up or concave down. Let's do an example. We're going to locate all extrema using the second derivative test. So we'll look at the function f of x is equal to x cubed minus 4x squared. So we use this on the concavity example in another video. So take the first derivative, 3x squared minus 8x, and we'll set that equal to 0. We'll factor out an x, so we'll get two places where the first derivative will be equal to 0. And that's when x is equal to 0, or x is equal to 8/3. Okay, so we're going to go ahead and find that second derivative, which will be 6x minus 8. And then we're just going to go ahead and plug in our horizontal tangent location. So one at 0 and one at 8/3. Now when we plugged in 0, we got -8, which indicates that we have concave down. So if we have concave down, we have a relative maximum of that location, 0, 0. And I found this I found that 0 right there by plugging it back into the original function. That wasn't too hard. F double prime of 8/3 is going to be 8, and that's positive, so we have concave up, which means we have a relative minimum. And I'll let you figure out what the location of, oops, go back. That should be 8/3, so let's fix my boo-boo there. All right. So that's where it's located. Relative min at 8/3, comma f of 8/3. Okay. Now we can move on. So we'll go ahead and graph this. There's our horizontal tangents where we've set the first derivative equal to 0. I think we said this one was at 0. That's the x value, and the x value here was 8/3. Okay. So I think we got maybe 2 more examples here. All right, so let's see what we got here. Okay, so it looks like we're going to do a parabola. And with parabolas from pre-cal, you put these things in vertex form. That was the negative b over 2a. That'll certainly work here. The nice thing about calculus, it allows us to do any polynomials, where the vertex form only worked for quadratics, but they are compatible. So I take the first derivative. There's the 2x plus 3. So we subtract 3 and then divide by 2. And there's our negative b over 2a. That's the x-coordinate of our vertex. That's the line of symmetry, or the axis of symmetry. That's where I have a horizontal tangent, according to the first derivative being 0. We'll go ahead and take the second derivative, which is not real exciting. It's just 2. And that's always positive, which means it's always concave up. And so at negative 3/2, of course, it's concave up. So we have a min at that point. It's a relative min. And in fact, because it's the vertex, it's going to be the global min or the absolute minimum. So we can certainly call it a relative min, and then we can also get a little bit more fancy and call it the global or absolute, meaning it's the lowest or the absolute lowest point on the graph. Okay. So again, take the derivative, set it equal to 0, and then you'll find a couple of numbers, maybe just one, like negative 3/2, and then plug it into your second derivative. Is it positive or is it negative? Okay. So I thought we'd do one more exciting one for the end here. So we're going to do 2 sine x plus cosine of 2x. And of course, we'll take the derivative. So it'll be 2 cosine x minus, and then because of the chain rule, we're going to have that 2 out in front, because when I take the derivative of the inside piece, I'm going to get an extra 2 there. Derivative of cosine is sine with the inside of 2x times the derivative of 2x. Okay. And since we're setting it equal to 0, we can divide both sides of the equation by 2, and then we're going to use a trig identity, a double angle formula. So sine of 2x is equal to 2 sine x cosine x. So we can solve this trig equation. We'll factor out a cosine x. We have 1 minus 2 sine x, and that's equal to 0. And I think I need to make some sort of restrictions, like we'll go from 0 to 2 pi or something like that. So we'll set each factor equal to 0. So cosine x will equal 0 when x is on the north or south pole, so that'd be pi over 2 and 3 pi over 2. And here at the top I'm mentioning my restriction, or what I'm going to limit myself to. And then sine of x is equal to 1/2, so 1/2 is smaller than the square root of 3 over 2, which means that your reference angle is 60 degrees. So that is going to be pi over 6, and in quadrant 2, 5 pi over 6, because sine is positive in the first 2 quadrants. Okay? Alright, so those are my numbers that I'm going to test. That's where I have horizontal tangents. Now, when I take the second derivative, I have to use this form, okay? We got to use that form. When I divided by 2, that's because I was just looking for the roots there, and that's not what the original function is. We still got that 2 hanging out, so we don't lose it. Okay. All right. So we'll go ahead and just rewrite the derivative of 2 cosine x minus 2 sine of 2x. And then we'll take the second derivative, so the first part's easy. It's negative 2 sine x. And then I'll pause it, and then if you want to do the next one, practice your chain rule, go ahead. Okay. So we're going to have an inside function, which is 2x. When you take the derivative, we're going to have an extra 2 hanging out, which is going to make this 2 turn into a 4. All right, so we'll have 4, and then derivative sine is cosine 2x. Although I didn't write a very good x there, so let's see if I can make myself a better x there. Okay, that looks better. All right, and now we're just going to plug and chug with all of our horizontal tangent locations, and we're just looking for positive or negative. Positive, it's a min. Negative, it's a max. Okay. All right. So I won't bore you with the computations. So when we plugged in pi over 6, we got negative, which means we have concave up, which means we have a relative max. And then you need to plug pi over 6 into the original function to find what the y-coordinate of that max is. Then a min at pi over 2, and then a max at 5 pi over 6, and then another min at 3 pi over 2. Okay. So that's the second derivative test, and we have a little bit more of a interesting example here with the trig functions. Okay. So it just takes a little bit of practice to get the hang of it, and you'll do fine.